Okay, so acids and bases. You should know some basic definitions, or at least be able to recognize some acids and bases. And if I asked you for a minute to write down what an acid and a base would look like, I'm hoping that perhaps some of you might write, well, that's an acid, that's hydrochloric. And then one of the bases that we use quite a bit, sodium hydroxide. And you should remember from last year that acids and bases react together to form salt and water. And this really could be viewed as a double replacement reaction, and you can write water as HOH, that hydrogen and the hydroxide. Now remember that salt, even though we think of salt as being sodium chloride, salt is a common term for any ionic compound. All right? So let's talk about some specific types of acids and bases and what those definitions are. An arrhenius acid is a substance that, when dissolved in water, increases the concentration of hydrogen ions. And so it's going to increase the concentration of hydrogen ions. We can also write that hydrogen ion as a hydronium ion. These are really interchangeable. We just sometimes write that because it's easier. All right, so acid, any subject that when I put it in water increases the concentration of hydrogen ions. A base, or at least an arrhenius base, is a substance that when dissolved in water increases the concentration of hydroxide ions. Okay? Before we get to the Bronsted-Lowry, you need to know strong acid these are acids that fully ionize in water, fully dissociate in water. Those acids are hydrochloric, hydrobromic, hydroiodic, the perchloric, the chloric, sulfuric, and nitric acid. These are all your strong acids. You need to memorize these. These are the ones where you need to know, if I see them in a formula or in an equation, that they fully dissociate into hydrogen and whatever the anion happens to be in that acid. Okay, strong base. The ones you need to memorize are the hydroxides of the alkali metals, that is group 1, and the heavier alkaline. Okay, so that would be calcium hydroxide, barium hydroxide, and strontium. Heavier group 2 or heavier alkali metals, meaning the ones at the bottom of that group. Okay, moving on to another definition, and these were just kind of getting the definitions out of the way. We're going to be using them much more shortly. Bronsted-Lowry. It kind of is a broader definition for an acid, and the definition is an acid is any substance that is a proton donor. That proton being that H+, that hydronium. A base is anything that's a proton acceptor. So the acid gives up the H+, the base accepts it. So a Bronsted-Lowry must have a removable or an acidic proton. A Bronsted-Lowry base has to have a pair of non-bonding electrons, so an unshared pair, so that it can accept that H. Now, there are some substances that can be either, meaning they can act as an acid or they can act as a base. Those things are called amphiprotic. Amphiprotic. They are also called amphoteric. It just depends on who's calling them that, right? They mean the same thing, right? Amphoteric can act as an acid or a base. Amphiprotic can donate or accept a proton. What does that mean? Well, it means that this hydrogen carbonate ion can accept a proton to become carbonic acid. Okay, it can also lose that hydrogen. Okay, so it can act as an acid or a base, and there are several things that can do that. If you notice, water is one of them. I hope I said that right. This way, accepting a hydrogen, it's acting as a base. This way, giving up one, it's acting as an acid. There are also things called Lewis acids. Lewis acids are defined as an electron pair acceptor. So the way I keep it straight in my head is if an acid is a proton donor, it's getting rid of a positive charge. So I remember a Lewis acid has something to do with either taking or giving up an electron pair. If an acid gives up a positive, it's becoming more negative, so it makes sense that it's going to be defined as the electron pair acceptor. The Lewis acid is a much broader term for acids and bases. So if a Lewis acid is an electron pair acceptor, atoms with an empty valence orbital can be Lewis acids. The bases then are electron pair donors. Anything that can be a Bronsted-Lowry base is a Lewis base. And hopefully you can see in the equation or in the reaction shown up here that this unshared electron pair is going to be shared with this BF3. Ammonia, NH3, is going to be donating its electron pair, so it would be the base. BF3 is going to be accepting that. It's going to be called the Lewis acid. So what happens when an acid dissolves in water? Water acts as the Bronsted-Lowry base and abstracts a proton from the acid. As a result, the conjugate base of the acid and a hydronium ion are formed. So this is going to be acting as the acid. It's going to give up this hydrogen to this water. If you notice, this Cl anion, chloride anion, is what is called the conjugate base of this HCl. The only thing different between the acid and its conjugate base is that the acid has one more hydrogen than the conjugate base does. We see here that this water is accepting that hydrogen, so it is a base, Bronsted-Lowry base, accepting a proton. Once it does, it is paired up with its conjugate acid. Okay. And this would be a pair. Okay. So in identifying conjugate acid-base pairs, you look for things that kind of have the same anion. Here I have the NO2, the nitrite ion. There's an H on this side of this compound with the nitrite ion, and over here that H is missing. So this has given up a hydrogen in the reaction, so this would be the acid. The anion that it is kind of paired with is its conjugate base. If you notice between here, the other two components, this water molecule has gained a hydrogen proton, to become this H3O+. This is the base because it's going to be accepting one, and then once it accepts it, it becomes the conjugate acid. reactions between acids and bases always yield their conjugate bases and acids. Okay, we're going to identify this in class, and we're going to be writing those in class as well. You should have them done for class. This is just a table that shows you a strong acid has a weak conjugate base. A weak acid is going to have a strong conjugate base. And this will help us when we start talking about equilibrium in acids and bases. Okay, so substances with negligible acidity do not dissociate in water. Their conjugate bases then are exceedingly strong. And remember, the definition of a strength of an acid and base is only that it completely ionizes or dissociates. So if I have a strong acid, it really doesn't set up an equilibrium. Theoretically, there is a little one, but it fully dissociates, fully ionizes. And the same with strong bases. So if I have a strong base that fully dissociates, its conjugate acid is going to be really weak. Thing to remember, in any acid-base reaction, we're going to have to say which way the equilibrium goes. And a rule of thumb, I guess just a definition, for any acid-base reaction, the equilibrium is going to favor the reaction that moves the proton to the stronger base. Since water is a much stronger base than the chloride ion, this equilibrium is going to lie far to the right. Hopefully that you identified this as being the strong acid, meaning it is going to fully dissociate, okay, into its H plus and its chloride ion. In this one, the acetate is a stronger base than the water, so the equilibrium actually favors the left side. In this case, we don't have a strong acid or a base, and we'll either have to use that table that was shown earlier to decide which way the equilibrium is going to shift, or we have to know a little bit more about the equilibrium constant, and we will get to that. Okay. So we'll do these in class. And this is where we'll pick up on the next screencast.